We don't live in a world that feels governed by quantum mechanics. If you ran into a wall, you'd just... But in the world of tiny particles, atoms and electrons, if they hit a wall, there's a tiny chance they can pass straight through it. That sounds impossible, but it's real physics, backed by solid mathematics. And without it, every star in the universe, including our sun, would go out. This strange phenomenon is called quantum tunneling. Imagine you're trying to roll over a hill. If you don't have enough energy to reach the top, you'd roll back down. Simple enough. But in the quantum world, particles like electrons don't behave like solid marbles. They act like waves spread out in space. Because of the Heisenberg Uncertainty Principle, we can't know both their exact position and momentum, so we describe them as a wave function as they move. These waves can overlap and exist in multiple possible states at once, a situation we call superposition. Only when we measure the system, when we observe it, does the superposition collapse, forcing the particles to take on one definitive state. Now, when this wave-like particle encounters an energy barrier, something that shouldn't have enough energy to cross, something amazing happens. Part of the wave is reflected, but part of it seeps through the barrier and appears on the other side. We describe this as quantum tunneling. It's not that the particle itself drills or teleports through, rather its wave function has a small but non-zero probability of existing on the far side of that barrier. And when we measure it there, that's where it appears. This behaviour can be described precisely using the Schrödinger equation, one of the most important equations in quantum mechanics. So what's the point of all this? Why should we care? Because without quantum tunneling, the sun would not shine. The sun's energy comes from nuclear fusion, where hydrogen nuclei smash together to form helium, releasing massive amounts of energy. But even with the crushing pressure and the searing temperature of the sun's core, around 15 million degrees Celsius, the nuclei still don't have enough energy to overcome the electric repulsion between the two positively charged nuclei. It's like two magnets repelling each other. There's a force between the two. Quantum tunneling provides a loophole. It allows some hydrogen nuclei to tunnel through this repulsive barrier, allowing them to fuse together. Each tunneling event is rare, maybe 1 in a million, but with countless atoms in the sun, it happens constantly, and that's why our sun burns brightly, and why we even have life on Earth in the first place. And quantum tunneling isn't just happening in the stars, we use it in technology too. For example, the scanning tunneling microscope can measure and even image individual atoms by detecting electrons tunneling between a sharp tip and the atoms themselves. Without quantum tunneling, that technology wouldn't exist. So next time you look at sunlight or see an atomic scale image, remember, somewhere deep down, particles are doing the impossible, tunneling through walls of reality itself. Don't forget to hit like, subscribe, and let us know if you have any quantum topic or any other science topic that you'd want us to explore next in a similar style video. Thanks for watching.